Hi everyone, my name is Johannes Dörfert. I work at Argonne National Laboratory, and I'm going to present our solve effort, or the more generic effort, of OpenMP compiler optimizations in the LLVM compiler framework today. Now, this talk is adapted from our LLVM developers talk that we gave a few weeks back. And if you follow this URL, you can actually find a recording of the talk. So this is overlaps quite a bit, but this time kind of my perspective on a couple of things and a little bit of updates as we speak, though the slides are fairly similar. Let's start. When you think about OpenMP and LLVM, what you usually think about is Clang's OpenMP handling. So you see the front end, it has an OpenMP parser, OpenMP semantic analysis, maybe with warnings and errors, and an OpenMP code generation part. That is what you usually associate with OpenMP and LLVM. Now, arguably, LLVM comes with a bunch of OpenMP runtimes, which are also part of the overall project. So there is libomp, which is the classic host OpenMP runtime, and there are offloading runtimes, some of which run on the host, some of which run on the device, all of which is kind of part of OpenMP in LLVM. Now, as many of you probably know, there's a second OpenMP frontend coming to the LLVM framework. So we will have Flang, or we already have Flang, as a Fortran frontend under the LLVM umbrella, which has an OpenMP parser, an OpenMP semantic analysis, and an OpenMP code generation. And as you can now see, that is a lot of repetition here compared to Clang. That is why especially the code generation part is split out into something that is called the OpenMP IR builder. It's front-end independent, and it favors simple and expressive LLVM-IR that can be analyzed and optimized better. And it's also reusable for non-OpenMP parallelism. That is either OpenACC, but also if you come from a different language that doesn't have OpenMP, you can still piggyback on the OpenMP runtime and optimizations. Now, what this enables us to do is really to optimize OpenMP as part of the LLVM optimization pipeline. The path that we introduced into LLVM 11 is called OpenMP opt. It is an procedural optimization path that runs by default if you specify O2 or O3, and it already contains host and device optimizations, though we are still working on more. So this is just like very early stages of this effort. But you can see that it's already in there. It runs by default, and you can see the results right now if you download LLVM 11. But you should keep in mind that this is an ongoing effort. And on the docs page that is linked, where the link is shown in the top left corner, you can, we're going to continue adding more information about this. So you should regularly visit the documentation page, and you should regularly build a new LLVM in case you're interested in new features, but also new optimizations. That said, the rest of the talk will be kind of specific about OpenMP opt. One of our very fundamental design goals here is that we want to report every successful and failed optimization. And this is something Joseph Huber from Oak Ridge is mainly working on. And how that looks, I can most easily describe with a simple example. So you have some simple OpenMP code, and you call a couple of OpenMP runtime functions, and you have a couple of directives. And what you can do, what the OpenMP opt path now does, is it actually eliminates some of these runtime calls if it can predict the result. What that helps you is you not only have less runtime calls, but you also have better static analysis afterwards, which is great for high-level optimizations, as we come to later. And if you want to know if something like this happened, you can actually run Clang and ask it for remarks, optimization remarks. So -r pass equal OpenMP opt gives you optimization remarks, and then if you also add -g, you get source locations properly. And as you can see here, it will tell you that there are these get thread limit calls that have been deduplicated. So you don't actually need to call it twice in a row. You just can call it once and use the result twice. That's basically what this says. However, as you can imagine, it is hard to express everything in these remarks, which are kind of command line short texts. What we really want to do is we want to communicate and explain the implementation details to the user in a way that is understandable and can be acted upon. Now, if we take a little bit more complicated example, but it's still really simple, and we run remarks on this one, what you will see is a wall of text, which is arguably not what you want. But it is really hard to describe these things in this text format on the command line. So while you see this, and if you want, you can read this and try to understand this, what will actually happen is we will build an OpenMP advisor, and we will build an OpenMP information webpage, documentation webpage. And the advisor, you can run it. It's part of the current JIT repository, will be part of LLVM-12. You can run it, and it will kind of summarize information for you, and it tries to kind of over time, it will help you to understand what is going on in a more interactive way, in a more user-friendly way. Until then, you can find optimization remark explanation, examples, FAQs, and so on and so forth on our documentation page that was linked earlier already, where we will gradually add them over time. So it's fairly new, it's fairly empty, but that is the place where these things will be explained. And while we are working on this kind of static angle, so statically providing better information to the user, we're also working on the runtime angle. So we introduced this libom target info environment variable that if you set it with any Clang build, it doesn't need to be a debug build or anything, but if you set it and then you run a target region, it will give you information about what is happening. So it will tell you about the CUDA blocks, the threads, the warp sizes, in what mode the kernel was launched, and so on and so forth. So a lot of kind of high-level information from the perspective of the runtime are provided here, though they are low-level from the perspective of OpenMP because it's about the implementation. But all of this will eventually be kind of exposed through the advisor interface and summarized through the advisor interface. Okay, let's switch gears for a second. On the static optimization side, one of the things we really want to do is we want to avoid people doing kind of manual low-level optimizations when they have OpenMP code. And we already did studies. We know that OpenMP code hinders various existing optimizations. So this is something that people tend to do to recover that loss. However, we can actually help here as well. And this is already built into OpenMP opt in LLVM, where if you have runtime calls, we can potentially predict their result, even if we don't deduplicate them, but we can just predict the result and replace them with the result instead. So if you look at this example, you have a parallel region and you call bar. If inside of bar, you check if you're in a parallel region. And what you can do after you inline this, for example, you can really say, okay, after I inline bar into foo, all this code that is not in the red part here can be deleted because we already know that we're in a parallel region, right? So this is a little bit of simplified view on this, but it gives you the idea. So all these internal control variables that are basically set and checked with these runtime calls, we can track statically and try to replace the getters with known values based on directives that we see and based on setters that we see. Now, while low-level optimizations and trying to kind of avoid these low-level runtime calls is great, but the main point of this really is to enable more high-level optimizations. So Jorgis works at Lawrence Livermore, and he is currently building various high-level optimizations into OpenMP opt. And what is most actively working on is the parallel region merging. So this is already inside LLVM, the current Git version. So if you download it, this will actually happen for you. So if you have adjacent parallel regions, you don't have to activate all threads, do the first computation, have a barrier, deactivate all threads, more or less like at least make them go to sleep somehow, and then activate them again for the next parallel region. What you can instead do is activate them only once and have like a pragma barrier instead in between. And we will actually work on removing these barriers as well. But the first step is merge these parallel regions, and that can be, as of now, we are in the process of extending that to allow sequential code in between. So where we guard the intermediate code, which can really help you in the long run, because it exposes optimizations inside these parallel regions, like inside these bigger parallel regions. You can now have more context to do optimizations, which was harder if you split them apart. Especially when we get to GPUs, this is also very helpful, because on GPUs, parallel regions work a little differently, and this will really lower the OpenMP overhead that people currently observe. Okay, now on top of these ICV trackings and these high-level optimizations, GPUs are very important. And one thing that comes up a lot is memory transfer latencies. Like where your memory is and when it is where is really important for you. And it is kind of hard to manage it manually. So what we're actually providing here are latency hiding optimizations. These are currently under development, parts of which is merged, parts of which is still out there. But I'm going to explain like two of the main ideas here. Go for the dev talk for a little bit more details. And if you're interested in any of this, just contact us. So the idea here is that if we see a mapping of data to a device, what we really want to do is we want to like issue that mapping, issue the memory copy as early as possible and wait for it to finish as late as possible, because everything that is in between of the issue and the wait is now executed while and hides the latency of the actual memory copy. So if we have this situation here, we have some computation that is kind of unrelated, and then we map some data to the device, and then we have a kernel. What we really want to make out of this is we want to first map the data to the device asynchronously. So we want to not wait for it to actually go to the device. We really want to just say, okay, issue the copy. And then later, we wait for the copy to finish such that we preserve correctness here. But now everything that is some computation, like in this some computation call, is kind of hidden, hides the latency of the data mapping. Now, obviously, you have to prove a lot of things here, but again, through the remarks, we can really interact with the user and use the the OpenMP assume directive to get the user to provide us with sufficient information to make these transformations happening. In this case, it was sufficient to really have the restrict on the pointer A, and we will be able to actually do this if the restrict is there. So this is not as far-fetched as it might seem. Now, if you have a situation where you actually map to from, which is the default for target, and then you do something like on the device, and then you come back, and then you map to from again, what you really want to do is you want to map to the device once, and you want to map from the device once. And what we're doing, like the way we develop this latency hiding technique, is really going to allow us later to remove copies altogether, not only to hide latency, but to remove copies under basically the same conditions as we hide latency. Okay, now when it comes to this memory transfer optimizations, one thing is really important here to see is that while we can do certain things while only looking at host code, at the end of the day, what you really want to do is you want to look at host code and target code at the same time. And if you look at a compilation flow of OpenMP right now in most compilers, including LLVM, that is not as simple as it might sound. For that to make that happen, Shilay is working on heterogeneous LLVM-IR modules, which is you can find a RFC on the LLVM dev list under this link on there. But I'm going to explain the general idea in like one very simple use case first. So let's assume you have some user code, which is a single C file, and OpenMP, everything is the host and the device code is in the same file, right? Now, what the compiler does out of this is it actually splits it into two files, like under the hood. It doesn't split it into C files as shown here, but for simplicity, you can assume that. And what it will do, it will try to offload. And if that fails, it will go to the host fallback code. And now if you take a regular compiler, what will happen in this case really is it will replace these uses of n in the host version with the constant value, but not in the device version. It will still kind of wait for the value to be sent from the host and then use that kind of variable value instead of the constant that we on the host side know. The problem is really the constant is part of the host code, not part of the device code. And that is unfortunate because these constants can obviously be very helpful when it comes to like loop trip counts, unrolling, vectorization, you name it. So what we're actually going to do is we're going to have a heterogeneous translation unit, like LLVM-IR file. Like here, it's again shown as C code. In reality, it's not C code, but LLVM-IR. But the idea is the same. So what it really says is there are now the same functions. Everything is more or less the same as it was before. The difference is that all these functions now have an annotation, which target they are compiled for. Target 0 for the foo function and target 1 for device function 7. So they are actually going to be compiled into different assembly, like one may be, let's say, x86, and the other one may be AMD GPU. But eventually we will probably split those again. But for the time being, we keep them in the same file, in the same scope, such that we can actually do this constant propagation across the device host boundary. And that will actually happen because we have these callback annotations already. And if you want to read up more about that, please follow that link to the callback annotations to see how this indirection is actually overcome through the callbacks. Okay. Finally, I want to acknowledge our support for the Solve is part of the ECP project. And as I mentioned early on, there were a lot of people involved in this, and I really reused the slides. You saw the names and the affiliations during the talk, and you should feel free to contact us. You should feel free to join our weekly meeting that we have about OpenMP and LLVM. We also have a dedicated OpenMP optimization and LLVM meeting that is frequented by people that are really interested in doing the actual work and not only just observing. Please reach out if any of this sounds interesting to you. If you want to participate, get more information, and I hope you liked it. And see you soon.